In this video, we're going to look at some examples involving curve and conservative vector fields, or not conservative vector fields, possibly. Okay, so here's our first example. Let f be the vector field 2xyz, x squared z plus z, and x squared y plus y. First, we're going to determine whether or not f is conservative. If we determine that f is conservative, we're going to find a potential such that vector field f equals the gradient of our potential. So first, we're going to use curl to see if our vector field is conservative. So the curl of our vector field, or del cross f, is partial x, partial y, partial z cross our vector field. So 2xyz, x squared z plus z, x squared y plus y. And when we cross that, we're going to get the derivative with respect to y, so x squared plus 1 minus the derivative with respect to z, so x squared plus 1. And then what are we going to get? We're going to get the derivative with respect to z, so 2xy, minus the derivative with respect to x, which is also going to be 2xy. And lastly, we're going to get the derivative with respect to x, so 2xz, minus the derivative with respect to y, so also 2xz, and that is going to equal 0, 0, 0. Therefore, curl is 0. The curl of my vector field is 0. Therefore, f is conservative. So the fact that f is conservative means that f must equal gradient of some potential, and we are going to find that potential. So we're saying that for a potential, partial x is 2xyz, partial y is x squared z plus z, and partial z is x squared y plus y. So let's start by integrating partial x with respect to x. Okay, so the integral of partial x with respect to x, well, that's going to give us x squared yz, x squared yz, plus we could potentially have some function of y and z, because if we took the derivative of that with respect to x, we would get 0. So the rest of whatever is in my function f, this would be some form of my function f of x, y, z, would be x squared yz plus something only dependent on y and z. Now I'm going to take this first version of our form of our potential, and I'm going to integrate with respect, I'm going to differentiate with respect to y. Take the partial derivative with respect to y. So I'm going to say f of y must equal x squared y plus the derivative with respect to y of g of yz. But I know that partial f, partial y, well, I've been given something for that. I know that this is supposed to equal what was given to me right here. So these two should be equal if this potential exists. So this must equal x squared z plus z, which then tells me the, oops, what's going on here? Where's my mistake? Oh, there's my mistake right there. This should be a z, not a y. There we go. The derivative with respect to y is x squared z. Okay, that makes a little more sense. Now, those two are going to cancel, and I get that the derivative with respect to y of g of yz must equal z. Okay, now let's integrate this with respect to y. So that means that g of yz should equal yz plus some function of only z. So let's call that h of z. Okay, I'm going to put this right back into my equation here. So this, I'm going to plug this back into my equation for f right here. So now I'm slowly putting the pieces of my equation for f together. I have f of x, y, z must equal x squared y, z plus y, z plus some other function that's only dependent on z. So now let's differentiate with respect to z. Partial z would have to equal x squared y plus h prime of z. But remember back here, I already have an idea of what partial z should equal. Partial z should equal x squared y plus y, which means that h prime of z equals 0. Now, if I integrate that, I get that h of z must be a constant. And that's the last piece that I need to plug back into my puzzle. What was h of z? So that is going to go right in here. And I have my potential f of x, y, z equals x squared y, z plus yz plus some function or some constant k. So you probably could have figured out what the potential was by sort of guess and checking, putting the pieces together in your head, but this is how you would do that systematically. So first we figured out that f is a conservative function by showing that the curl of f is 0, and then we found the potential of f using the partial derivatives. Okay, let's try another example. Is f conservative? We're going to let f be the function yzx. And if f is conservative, we are going to find a potential for it. So the curl of f is del cross f, which is going to give me partial x, partial y, partial z cross yzx. And what am I going to get? I'm going to get 0 minus 1, and then I'm going to get 0 minus 1, and then I'm going to get 0 minus 1. Well, this is definitely not equal to 0, and therefore f is not a conservative vector field, because the curl of any conservative vector field is 0 everywhere. Well, let's use this as an example for something else. What if I did not know that f is not conservative? I didn't bother checking that whether or not f is conservative, and instead I went straight to trying to find a potential function such that vector field f equals the gradient of that potential function anyways. So let's use the example. We did just figure out that it's not conservative, but let's try and use that anyways and trying to find a potential for this. So, if partial x is equal to y, then if I integrate with respect to y, I would know that f of x, y, z must equal xy plus some function of y and z. Now, let's say I now take the derivative with respect to y. Fy equals xy, x, taking the derivative with respect to y. So that's going to be x plus g prime of yz. Or I should more properly say partial g partial y of yz. Let's get rid of that. Okay. Well, I have what partial y should be. I know that partial y should be equal to z, which means the derivative with respect to y of g of yz would have to equal x or z minus x. Well, this is impossible. This is not supposed to happen. Impossible. G of yz can only depend on y and z. G of yz cannot have an x in it. You can't differentiate a function g of yz that only depends on y and z and get a result that's depending on z and x. So I have encountered a contradiction, and it's not possible that these partial derivatives represent the gradient of some potential function f. Therefore, a potential does not exist for this vector field that is not conservative.